Welcome to this comprehensive hands-on demo of KEDA, which provides intelligent auto-scaling capabilities for Kubernetes clusters. In this tutorial, we'll demonstrate how to implement smart auto-scaling using Google Cloud's Kubernetes engine, often called GKE. KEDA offers various options for event-driven auto-scaling, which you can explore in their documentation under the Scalar section. Our focus today will be on Google Cloud's PubSub service. We'll build a proof of concept that shows how to automatically scale Kubernetes workloads based on incoming messages from a message queue. This setup is particularly useful for scenarios where you need to process data via tasks that are triggered by incoming PubSub events, requests, or prompts. Let's begin with setting up our environment. First, we'll create a new Google Cloud project and set up a Kubernetes Engine cluster. Before we can create the cluster, we need to enable the Kubernetes API in our project. Once that's done, we'll navigate to the clusters page to create a new cluster. For this demonstration, we'll choose a standard cluster instead of an autopilot cluster. This choice is important because it gives us more detailed control over our setup, which is especially helpful when designing complex auto-scaling systems. In the cluster settings, we'll keep most of the default configurations, including keeping it as a regional cluster. While this option is slightly more expensive, it provides better availability. You have the option to reduce the node sizes if you want to optimize costs. On the security configuration page, we need to set up access for each API, making sure our Kubernetes cluster has proper access to the PubSub service API. We'll use the default service account for this demonstration, though in a production environment, you would likely want to use infrastructure as code tools like Terraform to manage your cluster configuration and related resources. After creating the cluster, we need to wait for it to finish provisioning. While we wait, let's prepare our development environment. We'll use the Cloud Shell Editor, which opens in a new tab and provides a full IDE experience. This environment is particularly helpful because it comes with pre-installed tools like kubectl and Helm, and it makes the authentication process much simpler. Before we can install KEDA, we need to properly configure our Google Cloud settings. This includes setting up the project configuration and authenticating with our newly created cluster. Once that's done, we can proceed with installing KEDA using Helm, following the official documentation. After the installation completes, we should examine what was installed in the new namespace. The installation creates several components: an operator, some admission webhooks, and metrics collection services. It's important to verify that all these pods start up correctly before moving forward. When we check their status, we can confirm they are all running as expected. Now comes the exciting part, implementing autoscaling with KEDA. When we examine the Google Cloud PubSub Scalar documentation, we can see that it provides extensive control over subscriptions, topics, and scaling behaviors. The system allows us to autoscale either deployments or stateful sets, though for our purposes, we'll focus on deployment-based autoscaling. This means we'll need to create a Docker container that can pull and process messages from PubSub. Let's build our application that will process the messages. While the application code isn't the main focus of this tutorial, we'll create a simple Python-based consumer that demonstrates the concept. Our application will pull messages from the PubSub topic and wait for 30 seconds before processing each message, simulating a workload. We'll configure the subscription name as an environment variable to make it easily configurable. For packaging our application, we'll use a basic Python container setup. The requirements are straightforward. We need a recent Python-based image. We'll copy in our requirements file, install the necessary modules, and then add our application code. One crucial dependency is the Google Cloud PubSub library, for which we'll specify the latest version available at the time of this recording. To run our application on Google Kubernetes Engine, or GKE, we need to introduce another service, the artifact registry. This service will store our Docker containers that GKE will use. These containers are what will be autoscaling to process our PubSub messages. Let's create an artifact registry repository in our project, making sure to place it in the same region as our Kubernetes cluster, US Central 1, to optimize image pull times. Once our repository is set up, we can build and push our container image. After building the image successfully, we'll push it to our artifact registry repository. You can verify the upload by refreshing the artifact registry page, where you should see your newly pushed image. Next, we need to create our Kubernetes resources. For authentication, we have several options. We could use the config connector to provision a service account, or we could use GCP access token credentials. However, since we're using a service account that already supports PubSub publishing, we can simply rely on the node's built-in authentication. We'll create two main Kubernetes resources. First, we'll set up our PubSub consumer deployment, specifying our newly created image. Then we'll create a scaled object for KEDA, which will control the autoscaling behavior. In our configuration, we'll set up a 1-to-1 scaling ratio, meaning we'll have one pod for every unprocessed message in PubSub. This direct correlation makes it easy to understand and monitor our scaling behavior. Before we can deploy our application, we need to create a PubSub subscription. We'll create it with a pull delivery type, which means our application will actively pull messages rather than having them pushed to it. Since our application waits 30 seconds between processing messages, we'll set the acknowledgement deadline to 60 seconds to prevent message timeout issues. When we first deploy our system, we encounter a small issue. We need to adjust our service configuration to remove the maximum concurrent messages setting, as we already have max messages specified elsewhere. After making this adjustment, we rebuild and push our Docker image again. During testing, we noticed that we're not getting enough logging information to effectively debug our system. To address this, we update our Docker container to include more detailed logging. After rebuilding and pushing this improved version, we can better monitor our application's behavior. With our improved logging in place, we can now properly test our system. When we check the PubSub page and look at the subscription metrics, we can confirm that our service is processing and acknowledging messages correctly. To test this, we publish a simple test message to our topic and observe our system's response. The logs show that our application successfully receives and processes the message. However, we encounter a challenge. When we submit multiple messages, the system isn't autoscaling as expected. Instead, it's processing messages one at a time, waiting for each 30-second processing period to complete before moving on to the next message. This isn't the efficient autoscaling behavior we're aiming for. Investigation of our operator logs reveals the source of the problem. We're seeing error messages about unexpected end of JSON input. The issue stems from our authentication setup. We're trying to use an environment variable to store access tokens, but this isn't the most effective approach. Instead, we need to switch to using native authentication structures, allowing the pods to use their built-in authentication capabilities. After making this authentication change, we see a significant improvement. The KEDA operator now successfully sets the target state and adjusts the deployment replicas based on the number of unacknowledged messages in our PubSub subscription. When there are no messages to process, our deployment scales down to 0 pods, saving resources. To verify our autoscaling is working correctly, we perform a final test by publishing several new messages simultaneously. The results are exactly what we wanted. The system scales up appropriately, creating one pod for each message that needs processing. We can observe the system creating 3 pods to handle 3 different messages simultaneously. Once all messages are processed, the system automatically scales back down to 0 pods, demonstrating efficient resource usage. Checking our subscription metrics confirms this behavior. We initially see 3 unacknowledged messages as the system spins up, but this number returns to 0 as our pods process all the messages. After processing is complete, we have no running pods, showing that our auto-scaling system is working as intended. For those planning to implement this in a production environment, it's important to note that you'll want to add some additional features. For example, you should consider implementing dead letter topics to handle failed message processing, along with other message queue management systems. These additions will make your system more robust and reliable in a production setting. If you'd like to support the channel, consider starting a free trial of our new design tool, which is linked in the description, and let us know what you think. We'll include all code and the diagram file in the description as well. If you have any questions, please post them in the comment section and we'll do our best to respond. Thank you very much for watching to the end, and please enjoy responsibly.